Hi, how's it going? My name is Carl Diaz with the Learning Resources Center here at the University of Colorado, Denver. And today we're going to be solving two problems here. Now I'm going to separate them. I'm going to make this video into two, but they're really just one problem. Okay, the problem, I separated into two, but your professors could ask this one way. They could tell you have a ball, okay, like a styrofoam ball, and it's tied with a rope at the bottom of the ocean or at the bottom of a cup of water or a swimming pool, whatever. All right, and they could say, what's the tension in that rope? And then what they could then ask you is say, when we cut the rope, cut the tension, what's going to be the initial acceleration of the ball? Okay, so that's how this question could be asked all at once. All right, I'm going to separate this video into two where we're solving it bit by bit, but keep in mind, and I'll remind you all through, this can be just one question. Okay, so we're told we have this styrofoam ball that it's in a fluid with the density, which is just normal water, of 1,000 kilograms per meter cubed. That's the density of the fluid. We know the density of the object, and we know the radius of the object. That radius, knowing that radius, when you're given the radius of the object, you know the volume of the object. But so just keep that in mind. Sorry about that. Okay, so. Like I said, the first question is asking us for tension. Also something to kind of good to keep in the back of your mind. Now again, that you go watch the concept video if you're really wondering where I'm grabbing this from. But it's important to keep in the back of your head as you work through problems with this. It's the reason how to apply Archimedes' principle of the buoyant force is that we always know that the buoyant force is equal to the density of the object times the volume of the object in gravity. Or more importantly, when we initially were deriving it, we knew that the buoyant force was equal to the density of the fluid, the volume of the fluid times gravity. Okay, so it's good to keep that in the back of your head because a lot of times you're going to see, we'll do it twice, we'll be replacing the buoyant force with this. And if you don't know that, that's the key to these problems. You won't know what to do. And the minute you know that, these problems are that bad, they're actually pretty straightforward. So what is tension? All right, well the first thing, just like with everything, we know our givens. Want to draw a free body diagram. So again, we have the buoyant force is up. Remember, the buoyant force is always pushing up on the object, right? The buoyant force comes from the fluid. It's another reason why we write the buoyant force this way, is the density of the fluid and object, right? That's where the buoyant force comes from. It's not from the object, right? And so that's always, especially when an object's fully submerged, we know that the buoyant force is equal to that volume of that object. All right. Anyway, sorry. And then we also know that that ball has weight. Weight's always pointed down just because this thing wants to float up here, right? Because it's a styrofoam ball. It wants to float up, right? But it's being tied down with this rope down here. So it's not going to. But the minute we cut that rope, it's going to shoot up just like we see in the next question, right? But here it's tied to the rope. So even though it's wanting to shoot up, the weight's still down of the object, all right? Weight is always down for every object. And then tension, we know is down. You need to recognize that. No, the tension isn't up. You should be asking yourself, why is tension down if you don't know why? And if you know why, then awesome. Why is tension down? Because that's what tension's doing. If you don't know, go watch the force video I made for you. I described, this is how you have to recognize the forces, right? Sometimes tension's pulling up on things, like a sign, right, that we hang from the ceiling. That sign wants to fall. We tie ropes to it and attach the ropes to the ceiling, and the ropes pull up on the sign so that it doesn't want to fall. Here, the rope's pulling down, right? The ball wants to shoot up, so the rope must be pulling down on the ball in order to not allow it to shoot up, right? So that's the idea here, okay? And that's how you know tension's down. You also know tension's there because there's a rope. So that's our free body diagram. All right, this thing isn't moving, right? It has tension. It's just sitting there. It's in the fully submerged in the fluid. It wants to shoot up, but it's not because it's being held by this rope, right? So we know that we're going to use Newton's first law because it's in equilibrium. Ball's in equilibrium, right? And then again, once we know what law we're going to use, we just use our free body diagram. It's just as easy as using this free body diagram. I forgot to put the coordinate system in here, but I'm not trying to do anything tricky to you. Just positive y is going to be up, negative y is going to be down for both of these. Just keep that in mind. I'm not trying to do anything tricky. So when we make this equation for this free body diagram, we know buoyant force is going to be positive. The weight of the object, and you want to make this MO, okay? It's very, very important that you're making that the mass of the object, because it could be the mass of the fluid, right? We talk like this in fluid dynamics and statics, so it's important to label the mass of what? Mass of the object, right? We know the mass of the object and tension are both pointing down, which is in the negative y direction. So those both get negative signs in here. Those are all the forces, so we know we can end the equation with 0. Now, once you have your equation, the first step that you can do here is they're asking for tension. Well, let's solve this thing for tension, right? But when we solve it for tension, and this is the thing I want to point out here, because we could have solved this a slightly different way, but is that we look at this equation. Now that looks great, right? Buoyant force, mg. Man, if we had that stuff, we don't have that stuff, we would have tension, right? But the other thing that you should realize is this isn't really written in terms of fluid statics or dynamics. It's written in terms of solid statics, right? Like if I went and pushed a solid object, this is how we see equations for solid objects. For fluid dynamics, we typically represent things you see a lot of times, and I have here, the mass will typically be equal to the density of the object or fluid and the volume of the fluid, right? That's just coming from the typical equation that we know density is equal to mass over volume. So if we rearrange this equation for mass, we know mass is equal to density times volume. And we know that we gotta put, mass should represent this density times volume if we're trying to talk about fluid dynamics here. Density should represent, the mass of the object should be represented this way. So that's one reason why we know we can't stop here and it's not good. The other reason that we know is buoyant force. Unless we were asked to solve for the buoyant force, then we can keep this FB. But since we're needing to use the buoyant force to solve for tension, we're asked for tension, so we need the buoyant force, we should probably change it over to again, another way to represent buoyant force in terms of fluid dynamics, which is the density of the fluid, volume of the fluid, and gravity. And that's exactly what we do. So when we replace the mass of the object by density and volume, we get this equation, the density of the object, volume of the object times g. We replace the buoyant force with the density of the fluid, volume of the fluid times g. We get this equation. Now, if you're asking yourself, where did that come from? Why is buoyant force equal to the density times fluid times gravity? That's the point of those concept videos. Go watch the concept videos. I explain all of that in there. And these, as much as you want to just come watch a question and see how it's solved, it's not going to help you unless you watch those concept videos, because the problems are only solved because of the concepts. Okay, so go watch the concept video. You know why this is. You know why we can do this and why you should be doing it and why it should be in your head every time you're doing fluid dynamics. The buoyant force is this. When we look at an equation and see densities and volumes and stuff, we see this is more representative of fluid dynamics, an equation that's going to help us in terms of some sort of fluid statics or dynamics, and this is perfect. And there's tension. That's tension. All right. The thing is right. We have the. Do we have the density of the fluid? Yeah, right there. Density of the object, we have it right there. Do we know G? Yeah, G is 9.8, right? Do we know the volume of the object? Yeah, the radius, right, is if we know the radius, we know the volume of the object. What about the volume of the fluid? Do we know that? We do. You might be saying, no, it's not up there. But if you remember Archimedes' principle, right, you know that when a volume is, an object is fully submerged, you know this to be true, the density of the, G's in there, but what you know to be true is the density of the fluid and the volume of the fluid displaced is equal to the density of the object and the volume of the object in the fluid. And when it's fully submerged, these volumes are equal, which means we do know the volume of the fluid because it's equal to the volume of the object. So if we know the volume of the object, we know the volume of the fluid. All right? So that means we have all the variables in there. We're done. We know tension. Okay, now again, if you're confused, you need to go watch the concept video that describes where that comes from, why we know these volumes are the same. Because if you don't know that, you're going to sit there and look at this problem and look everywhere for the volume of the fluid displaced. It's not going to be anywhere to be found. It's in the concept to know that these are the same when it's fully submerged. When it's not, go watch the video that I did for you that explains when objects are floating, when they're not fully submerged. These two questions are about fully submerged objects. When that's true, this is always true. These volumes, the volume of object and volume of fluid displaced, will always be equal. Okay, now keep that in mind when we solve this problem too. All right, I'm going to reiterate that, but it's always important, all right, to remember. That's how you apply that. So because that's true, right, for fully submerged objects, I have it written right there, we just factor out volume and G out of here because they're going to be the same thing. So this volume, right, you'll use the volume of a sphere. This is a sphere, right? I should have had that written up here, but you can look up the volume of the sphere. I think it's like 2/3 pi r squared or something. I don't want to write it up here because I don't think that's correct. It's definitely, one thing you should always have in your head is that if you're looking for volume, you know different volumes of objects are going to have some number here that's going to vary in and out, 2/3, 1/3. But the one thing you'll always know is that it'll always be times pi and then r cubed, the radius cubed. And why do you know that? Because volume, you always know that volume, it has the units of meters cubed. So the radius is the one with the units of meters, so that's going to be cubed. So you know volume's always pi r cubed times some number. So I know for a sphere, I can't remember. I should have written it down before I did this video. I'm sorry, but you can go look it up. It's like 3/4 pi r cubed or something like this. Okay, but we know that, so you can put that in there, multiply it by g, subtract these two numbers and multiply it, and you have tension. Okay. Now I said I'm turning this into 2 videos, but keep in mind the next question here, because this could be asked all at once, is now that you have tension, they'd be like, now what if you cut the rope? What's the initial acceleration of that object? That's going to be the next video we're going to look at, okay? But I'm going to stop this one here so that I can kind of separate them on the list so that you can see them as separate things. But I want you to know that this can be the same question. So I'll see you here in about 2 seconds when I start the second video, and we'll talk about this next one. Hopefully that was helpful. If not, go back and rewind and watch the concept videos, all right? I'll see you on the next video.